Oh, great. Meeting is now being recorded. Awesome. So thank you to Go, 12 years old. That's really fantastic. So happy birthday to Golang. So real quick about my employer, and then I promise this talk is really focused on JSON Web Tokens, not about FusionAuth at all. We are a drop-in user data store and authentication service. So competitors are Auth0 or Okta, things like that. We have different editions, including a community edition, which is free as in beer, and that supports multiple different grants. It supports SAML. It has other user management features like registration and passwordless and a lot more. And how that's relevant to this talk is that we do produce a whole lot of JSON Web Tokens. Real quick about me, who cares? You didn't come here to learn about me. My Twitter handle's down there if you want to learn more about what I tweet about. And you can Google me if you want. If you have questions, go ahead and drop them in the chat. I do have the chat window open. And then I do have a little bit of swag to give away. In addition to what Ari mentioned, I can ship anybody in the US, continental US, well, no, anywhere in the US or Canada a shirt. So if you want that, I'm gonna let Ari kind of handle giving that away at the end, probably the same time as he does the JetBrains stuff, but we'll need shirt size and mailing address, obviously. All right, let's get into the content. So JSON Web Tokens are a IETF standard. They're actually pronounced JWT instead of JWT, or I guess you could say JSON Web Token. That's precise too. But it's about 12 or 14 pages, and it was standardized, I want to say 2016 or 2017. And there are two kinds of JSON Web Tokens. There are tokens that are signed, which means that you can cryptographically determine the veracity of the content, but the content's not secret. Or there are JSON Web Tokens that are encrypted, where the content, the payload is actually hidden and it's encrypted in a way that you have to have the key to view. I'm going to talk mostly tonight about signed JSON Web Tokens because those are far more common in my experience. But you should be aware that encrypted web tokens, JSON Web Tokens, exist out there too. So in the context of FusionAuth and a very common context, JSON Web Tokens are used as stateless portable tokens of identity. Let me break that apart. That's a mouthful. They're stateless in that, as I alluded to earlier, you can determine the provenance of the JSON Web Token, whether it's been modified or anything like that, without communicating with an additional server. So that means you can basically, if you hand a JSON Web Token as a client or as someone who's consuming a JSON Web Token or some service that's consuming a JWT, you can know that it is a valid JWT without ever reaching out to a server to say, hey, is this valid or not? They're portable because they can be turned into URL-friendly strings. And we'll see an example of that in a bit. And then they're often used to represent an identity. They could, I mean, they're basically JSON objects, hence the name JWT, JSON Web Token, but they're often used to, especially by identity providers, to say, hey, the holder of this JSON Web Token is this entity or is this person. That makes them great for APIs. They can be used as bearer tokens. And one of the nice things about JWTs is that a lot of identity providers, FusionAuth and others, produce them. So you can have the identity provider authenticate the user, hand this token, and this token can then be passed around to other services who can rest assured that the holder of that token, except for in certain circumstances, is that entity. All right, so here's the application we're going to be walking through in this meetup presentation. So we have a to-do application, and this is probably an overly complicated to-do application, but it is a user. You have a user service or API, and then you have a to-do API, and then you have clients over there on the left that communicate with those services. And then obviously on the right, you have the data stores for these different services. The user's data store looks a little bit like this, right? Mapping users and roles. And then the to-dos data store just has a list of to-dos. If this is stored in a PostgreSQL database or another relational database, that to-dos table might look a little bit something like this. And what's important to acknowledge is that user ID is not a foreign key because these are separate services. It's going to be, you're not going to be able to have that referential integrity. So let's walk through this application. The user posts some credentials to the user API. The user API verifies those credentials, and it typically is username and password, but it could be a lot of other things. It doesn't really matter. We don't really care. The point is the user API magically does its verification of who this user is. And then it gets the user's data from the data store and then passes it back to the client as JSON. That JSON might look a little bit something like this, right? It can have an identifier, name, email, roles, other information that's useful to this application. Then we're going to want to get our to-dos because people don't care about logging in. People care about changing their to-dos, adding new to-dos, marking them off. That's the best part, in my opinion, with any to-do list. So the client is going to have to request the user's to-dos. So in this very naive implementation, which you should not implement, the client takes the ID from the JSON that was returned to it and passes that to the to-do API, which then looks up that ID in the to-dos database and hands back all those users' to-dos. That gets sent back to the client, and the client can then render it, that JSON as it sees fit. So why is this a bad idea? Well, it's a bad idea, as I'm sure some of you noticed, because a malicious client or a misconfigured client can pass in the wrong user ID and therefore get back the wrong to-dos. And we need to keep things like, hey, Dan, go get milk after this meetup presentation, very safe and secure. So we don't want people to be able to look at my to-dos, and I shouldn't be able to look at anybody else's to-dos. So hopefully we made that diagnosis of that security, that fundamental security issue, we found that out before we started building anything out. So let's look at two alternatives that actually solve this problem. The first is what I call the opaque token solution. And so in this case, we have a token, which is just a string of random characters that is generated after the user logs in, and it's passed down as part of the user data to the client. The client then passes that token to the to-do API. Now this token represents a valid user somehow, but it's not a user ID, because if it was a user ID, then again, it could be enumerated, or people could try to guess valid tokens that pointed to the to-dos database. Instead, this is just an ephemeral string that is pretty much representative of the session of the user. So the to-do API doesn't have any idea what to do with this token, but it knows something it does know what to do with this token. And so it can call into the user API and say, hey, I got this token from this client. Is this a real token? Is this valid? Okay, if it is, the user API will hand back JSON. If it isn't, the user API hands back some other status code, and the token or the to-do API says, basically tells the client, hey, I'm not going to give you any to-dos because you gave me a bogus token. But if it does get back the user object, then it can pull off that ID and get the to-dos for that user and then pass them back as JSON to the client. So the difference here is that the token is out of control of the client. The client can try to manipulate it, but chances are high, if it's a string with a lot of entropy, it's not going to be able to come up with another valid token in a reasonable period of time. So this has a couple of problems. It is a valid solution, but it does couple the user API to everything. And as you add more and more APIs, if they need any user data, they're going to have to keep talking to the user API. And it's not just kind of a one-off. It's like every time that token is presented, because hello, looks like someone accidentally muted me. No worries. So you have this coupling, and then you also have a lot of communication with the user API. In addition to the fact the user API now has to like store this token somewhere and keep an idea of the state of that user. So JWTs are an alternative implementation, and we're all, anyone who's an engineer knows that there are trade-offs with each type of implementation. JWTs have their strengths and weaknesses. So let's kind of walk through a JWT implementation. In this case, the user API creates a JSON Web Token or a JWT and passes it down, and that JWT is presented to the to-do API. And the to-do API at this point needs to validate the JWT, which it can do by checking the signature. And it also needs to look at what's inside the JWT. But the difference here is that it can do that validation without ever talking to the user API. And that JWT can contain things like an identifier for the user. And because it checks the signature, it can be sure that the client, while the client might be able to read it because it's a signed JWT, the client won't be able to modify it. And that gives it the to-do API the assurance that it doesn't actually have to go talk to the user API. So let's talk about some benefits. As I mentioned earlier, it can be signed. It can be signed either by a public-private asymmetric key pair or a symmetric key. And we'll talk a little bit later about how you kind of do each of those. The validation is really critical. That's that stateless aspect of JWTs. And then the other nice thing is because it's a JSON object, it isn't just, it can contain other interesting information. And that can make it something that's valuable for your application because you can have more things in there than you might if you used an alternative solution like the opaque token, or even an API key or something like that. So let's look at a JWT. So we have, this is a signed JWT here. We have three components. We have a green header, we have a blue payload, and we have a tan or white signature. And each of these, or the first two, the payload and the header, are actually just base64 URL encoded or URL friendly JSON. So you can take them apart. You can cut and paste this into a base64 decoder, and you'll see the JSON object below. The header contains metadata. So that's what algorithm was used to sign the JWT and other information such as that. The payload is where things get really interesting. So the keys of this JSON object are called claims, and that's because they make claims about something, the entity the JWT was created for. So there are some claims that are standardized and some claims that are not. The four top claims here are standards. So they're in that RFC that I mentioned way back at the beginning of the talk. ISS is the issuer. EXP is the expiration time. Because JWTs are stateless and you don't have to refer to a central server, you need some way to determine for them to be invalid. And so basically they're invalid past a certain span of time. The odd claim, AUD, is the audience. So that is who this JWT was intended for. So the issuer in our previous architecture diagram was the user API. That is the entity that issued the JWT. The odd claim would be the to-do API. That is who should consume that JWT. The subclaim is who the JWT is about. So that's in this particular case, it's about me. And then the name and the roles claims are just to show that you can put other data in here. You don't have to just be limited to the standardized claims. And the roles claim shows that it can actually be a relatively rich JavaScript object. So you can have an array of arrays or whatever else you need. Anything that can be represented by JSON can be put into a JWT, as long as you're comfortable with it being visible to anybody who gets a hold of the JWT. The signature is the signature. And nothing special about this, but it is what determines, this is what gets checked to determine that the contents of the JWT haven't been tampered with. How that works at a very high level is when you're creating a JWT, you take the header and the body, you concatenate them together, you run them through a cryptographic algorithm with a secret of some kind, and then you pass that, and then you turn that into a string, right? That the results of that algorithm, and then the person consuming the JSON Web Token can do the same thing in reverse. If it's a symmetric key, or not the same thing in reverse, the same thing, right? They can take that header and that body and then run the same algorithm and then see if the signature string comes out the same. If it does, awesome. The client and nobody else tampered with it. If it doesn't, then immediately you shouldn't do anything else with this JWT because you aren't sure what's happened to it. So the end goal is, of course, for the To-Do API to be able to run this query against the To-Do's data store to get that JSON back to the client. So JWTs are often used as bearer tokens, and a bearer token is very similar to a car key. So that means that if I hand my car key to Ari, he can, and he's next to my car, he can hop in and turn my car on. My key doesn't know anything about who is holding it. That access to the key is what determines access, not anything else. So that means that if someone steals your JSON Web Token because you have left it in a log file, or because you are storing it in local storage, or for other reasons, then they can present themselves as you for the length of that token. The upshot of that is be careful where you store your tokens and keep them short. Keep them short-lived. Where we recommend at FusionAuth for token storage, we recommend storing it on the server side if possible, and then just using the session to identify the client. So the client presents the session cookie, and then your server-side code can then take that JWT and present it around where it needs to go based on what's in that session. That doesn't work for everybody, we understand. So if you're going to send it down to the browser, send it as an HTTP only secure cookie. This keeps it out of JavaScript's meddling hands. And if you're sending it down to a mobile storage place or a mobile app, put it in secure storage. There are some standards out there that can tie a token to a particular client. Depop or MTLS are the two standards I know about. So if you're interested in that level of security, where you're no longer using a JWT as a bearer token, but it is kind of a more secure key, or sorry, a more secure, what's the word? Proof of identity that can't be kind of picked up and used by anybody who finds it. Those are the standards you want to look at. So there's a lot of, there's some foot guns with JSON Web Tokens. They're very powerful specification. So I'm going to run through some of those. Definitely use a library if you can. Go has a pretty nice library that actually was maintained for a number of years by somebody and just got taken over by the community, I think in April. You want to verify your claims. And I'm going to run through some code real quick about that. So I think I have to stop sharing because I share entire desktop. There we are. All right. So can someone give me a thumbs up if you can see my terminal? I just want to make sure I got that right. Great, thank you. So in this this code, which is available in on GitHub, and it's Apache licensed, so you can pull it down and play with it if you want. We have this code basically encapsulates the user API and the To-Do API in the same place, in the same kind of code, in the same basically Go program. You're not going to do this typically, but it's good for a demo. So lines 11 through 37 are where I am creating the JSON Web Token. I'm signing it with that signing key on line 11, and I'm going to print it out. And then I can decode the token, right? I can receive the token string and I can decode it using this code. And the interesting parts of this code to me are, the decoding section, because again, you're probably not going to be creating JSON Web Tokens very often. You're probably going to use an IDP or something else to do that. So lines 43 through 50 are pretty much using the library to check the signing method to make sure that we are, the signature, to make sure that it wasn't tampered with over the wire. And then we also look at our expected claims. And so that's what I mean by verify your claims. You want to make sure that you are checking the audience to make sure that you are the intended consumer of this JSON Web Token. Because if you're not the intended consumer, then the contents of that JSON Web Token might not mean very much to you. The roles for a forum software are probably different than the roles for a custom application or a piece of banking software. So even if they're all signed by the same IDP, you probably you don't want to be consuming a JSON Web Token that isn't created for you. And then you also want to make sure that you're verifying the issuer, just so you're not consuming a JSON Web Token that is created by somebody that you don't expect. That's pretty unlikely because the keys would probably be hard to be matched up to, but it's definitely better to be safe than sorry. Cool. So let's go back here. Now, and as I said, that code is available, and there's several other bits of JWT related code that are in that repo. JSON Web Tokens can contain arbitrary JSON data, but if they're assigned JSON Web Token, don't put any secrets in there. Don't put any social security numbers or anything like that, because anyone who finds that token can decode it. It looks like, code, but it's really just base64 encoded. And so that, again, I just want to drive this home. If you take one thing away from this talk, it would be, if you have a signed JSON Web Token, anybody who gets it can see the contents of it. If you use the HMAC algorithm, which is the symmetric signing algorithm that is supported for JWTs, you want to make sure your secret's nice and long, because there are programs out there. This is one that actually will take just a JSON Web Token and will just try to brute force it so that it can get that key. And if it gets that key, if it can brute force the key, then it will be able to sign JSON Web Tokens with that key, which is obviously a negative situation. Another foot gun that always comes up when I post on Hacker News about JSON Web Tokens is there's a none algorithm. And that means that no signature is required. And that turns this JSON Web Token into this one, or something similar to it, right? So there's still 3 clauses, but there's no last signature clause. The header changes a little bit to alg none. And that means that anybody who finds a service that accepts a JSON Web Token, a JWT, that doesn't check the signature, can craft any payload they want and put it into and base64 encode it and pass it to that service. That's obviously not great, right? You're not just talking about unsanitized input, which we're all supposed to be careful of as developers. You're talking about unsanitized credentials, right? This is the JWT represents who I am. If you accept alg none signatures, then I can be whoever I want to be, right? I could be the I don't know, who would I want to be? Wizard of Oz. I could be the Wizard of Oz if I wanted to. I could create those credentials, which obviously is a really bad idea. So you want to make sure that you, as a consumer of a JSON Web Token, don't ever accept anything that's signed with alg none or that doesn't have a signature. The spec allows this, and the simple fix is, as I mentioned earlier, don't allow none. And the reason why it is in the specification is actually because there are other ways to verify a JWT is unchanged. And, it could be a private network, it could be client certificates. And if you are in a situation that there are 2 criteria that you should meet before you ever allow alg none. The first is that you have this other way to verify the JWTs are unchanged and that you trust your clients. And the second is that you have benchmarked it to determine that the signature of a JSON Web Token is enough of takes enough time that impacts your system negatively. All right, let's talk about signing with asymmetric key pairs. So some of the examples before were signed with HMAC, which is a symmetric key pair, and that means that both the user API and the to-do API need to have access to that shared secret. The first to sign it, the second to verify it. So that means that if you are trying to make sure that you are securing this thing that is used to sign basically credentials, right? Distributed credentials, which is what a JWT essentially is, then you need to make sure that you protect both the to-do API and the user API. Because if someone gets a hold of that shared secret, again, they can sign JWTs, so they could like put whatever they want into that JWT, give themselves the role of super admin, and then sign it and then pass it to your system, which is a negative situation. So if you use a shared an asymmetric key, then let me step back here. If you use an asymmetric key, the private key stays in the user API and the public key is used to verify the signature. And that obviously reduces the amount of surface area that you need to secure to keep that key and the ability to create arbitrary JWTs safe. It also scales organizationally. And what do I mean by that? I mean that the user API can be run by one department and many other departments can consume the JWTs that are created by it. And if the user API folks decide they need to rotate keys, they can do so, and they don't have to find some way to share a secret with, you know, the 10 other departments that are using it. In fact, the user API, the identity provider, and the APIs that are consuming the JSON Web Token don't even have to belong to the same company. As I mentioned earlier, it also changes your security radius. And then key rotation is easier. And we'll see a little bit about that in a second. It is a more complicated system and it's slower. And I've run some benchmarks, not in Go, it was in Ruby, but it was between 2 and 10 times slower. So that's a trade-off. So when the JSON Web Token is presented to the to-do API, the to-do API needs that public key to verify it. How can it get that public key? Well, you can deploy the to-do API with the public key on its own file system. And this has a benefit of basically really severing that connection between the user API and the to-do API. They can live on totally different networks. There could be no network path between the to-do API and the user API if you deploy the primary key or the public key. It has some downsides too, because rotation is harder. If, on the other hand, and this is more common, the to-do API can connect to the user API over the network, it can pull down a list of the public keys, because again, they're public keys. The user API can publish them, and doesn't really care who knows them. So it can publish those, and the to-do API can once in a while pull down those public keys and then use those to validate the private key. How does it match between them? Well, here's a thing that is probably pretty hard to read. This is a sample output from that JWTs JSON file, which basically just lists the public keys. That's another standard. I think 70. Don't quote me on the number, but JWTs is a standard. So you have this information, the algorithm that this key corresponds to, a key identifier, and then the actual PEM file or the PEM content of the public key. If you have multiple keys, which you probably will, then a JWT can be signed with a key identifier. So this is that header that we talked about earlier. The key identifier is going to map to one of the public keys that is in that JWTs.json doc. So yeah, so you can see that we can have n keys, And so you can see how rotation would work really easily in this situation, because basically what you do is you want to rotate out the key that starts with UK0. Well, what you do is you create another key. You might start with UK1, and then you start signing JWTs with that key. And then after a period of time has expired, right? However long the JWTs that you signed, however long your JWTs are signed for, like 5 minutes, 10 minutes, after that period of time is expired, you can actually delete the key that starts with UK0. So that's how rotation would work. Refresh tokens are a key part of any JWT-based system, no pun intended. And what they do is JWTs are supposed to be short-lived. Refresh tokens can live for a long time. And refresh tokens are basically used to mint new JWTs. And you use refresh tokens because because JWTs are stateless, you have kind of two unappealing alternatives if you don't have refresh tokens in the picture. The first alternative is that you have very short-lived JWTs, which is very secure, but anytime a JWT expires, the user has to re-authenticate and go back to that user API and say, hey, I'm actually Dan, here's my username and password. That's not great UX. The alternative is I'm going to have long-lived JWTs, days, months, years. Well, now, if anybody finds that JWT, then they can use it for a very long period of time and for whatever sinister purposes they may have. So refresh tokens basically let us have the best of both worlds. So how does this work in practice? Well, what we have is basically the user API creates a JSON Web Token and a refresh token at the same time and passes those back to the client. The client now presents that JSON Web Token to the to API. And let's say our token's good for 5 minutes. So for 5 minutes, we're making all these requests, everything's hunky-dory. Then at the end of 5 minutes, the to API, when it's validating the JSON Web Token, notices it is expired and therefore the access is not granted. The client can notice that request failure and say, well, I have a refresh token now, so I know my JWT is no good, but I'm going to present my refresh token to the user API. The user API can look at that refresh token, determine that the user is still a valid user in the system, and create a new JSON Web Token. That gets passed back to the JWT, and then the JWT is good for a new JWT is good for another 5 minutes, and that's what's presented as the Jew API, and the user has been basically silently re-authenticated without ever being bugged for their username and password. By the way, that means that refresh tokens are very powerful, and you should secure them at least as well as you secure your JWTs. All right, talking about distributed systems a little bit, if you're going to be deleting your users, you don't have on delete cascade anymore. So what are you going to do? You can actually set up webhooks so that interested services can be notified when a user is deleted, and then they can do that cleanup, right? So the client sends a delete request to the user API fires off webhooks to all the different APIs that are part of the system that have user data. Those APIs or services can then do the deletion of user data from their data stores. When you're talking about logging out, it's really about revoking the refresh token. It's not about revoking JWTs. We'll talk in a little bit about revoking JWTs, but really what you're doing is you're revoking the refresh token in a JWT-based system. So what does that look like? The user clicks log out. The client fires off a request to the user API, says, hey, this refresh token is no longer good because the user's logged out. And then they delete the JWT and the refresh token from their storage system. So can you revoke JWTs? The answer is sort of. You have a couple options. You can, if a user's JWT has been stolen, or you just want to make sure that JWT is invalid, you can rotate your keys. And if you rotate those keys without leaving the public key the corresponding public key available in that JWTs doc, then if somebody comes in and the jot is signed with a certain key identifier and that the corresponding public key can't be found, it's going to be an invalid jot. So that is one option. It does have the effect of basically invalidating an entire class of JSON Web Tokens, every JSON Web Token that was signed with that key. You can wait it out, which isn't really a way to revoke things, but it is a valid choice. You can also make jot lifetimes pretty short. So that is one choice to deal with this situation. The kind of middle ground is to maintain a deny list. And so what this does is actually pushes state back into the APIs. So they're now responsible for things like keeping track of a list of invalid APIs, invalid jots. So every time a refresh token is revoked, which basically means the user's logged out, there's a webhook fired off, and the To API can keep a list of those webhooks. So when it's doing its jot validation, it doesn't just check the audience, it doesn't just check the expiration time, it doesn't just check the issuer and the signature. It actually will check this stateful list of jots that have been invalidated. And if it finds a jot identifier on that list, then the To API should treat that just the same as the jot has expired. So as far as jots in Golang, I hope, so first I'm wrapping things up. I hope that this has given you a good idea of when it makes sense to use jots and what the trade-offs are with using them. If you're thinking about using them in your Golang program, I would just say, look at the jot library, right? Look at the jot module and, oh, it's actually library, sorry. The library is, as I mentioned, relatively new in terms of where it lives on GitHub, but it is old in terms of the code, right? So it's really well-written, battle-tested code. Make sure you check your claims like I showed you in that sample code. If you're checking it, if you're doing it kind of at the authorization level, then depending on how your Golang code is written, you could use a filter if it's coming in over HTTP. You also can leverage, there are a lot of gateways out there they can plug in and do some jot checks. So I know Kong does that. I'm working with HA Proxy right now. So you can basically check a JSON Web Tokens claims before your services ever see them, if you want to kind of externalize that level of validation. So a few more tools. There's that code that I said was available. I've written a couple thousand words on building a secure JSON Web Token, and I'll make these slides available. I'll send them to Ari after, or maybe I'll just post them on the meetup after probably tomorrow morning. So just want to say thank you. That's the end of the presentation. If you want to learn more about FusionAuth and how we think about OAuth, there's a free ebook. It's about 80 pages, talks about jots and OAuth scenarios we've seen in the real world. And then I will expect to hear from Ari about the t-shirt. So if you want a t-shirt, make sure you DM Ari and say, hey, I'm interested in being in the drawing for the FusionAuth t-shirt. And thank you. And I will take a couple of minutes of questions if we have time.
Thanks, Dan. Well, actually, I'm gonna make my life easier, Dan. What I'm gonna do is I'm actually just send me your email address, and what I'm gonna do is I'm gonna forward your email information to Dan, and then you'll exchange personal information there, as opposed to me taking addresses and shirt size. You can work with Dan on that directly. But what I'll do is I will be happy to put your name on. I'm going to put everyone that sent in for the JetBrains into the contest already, unless you just refuse to take a t-shirt from Dan. And how many pieces of swag are you giving out, Dan?
Just a t-shirt.
Just one t-shirt? One
t-shirt.
Okay, yep. You got it. So one person will win a t-shirt, and Dan will send it to them, and we'll do a wheel spin at the end for that. So just send me if you would like to be in that as well. Thanks. And any questions for Dan that you want to either put in the chat, or feel free to take yourself off mute and ask directly.
Awesome. I must have killed it. Well, thank you all. I really appreciate the chance to talk to you, and congratulations on the renaissance of your meetup group. So
thanks, Dan. We really appreciate you taking the time and coming out and sharing with us. So before we go on to our next speaker, I want to two things. One is I'm going to put the Jfrog Raffle I mentioned before. I just dropped that in the I call it the Slack, with the chat, for those who want to enter that. And also, I already told you to send me your email address if you'd like to be in a spin for the t-shirt. And also, I'd just like to introduce our next speaker. It's not like I'm using a teleprompter or anything, but I want to introduce to you Sudhindra Rao. Currently works for JFrog as a development manager to help build communities and partnership to provide visibility into JFrog's liquid software mission. He's been working as a developer and architect for critical business applications, developing in multiple languages, including Go, Ruby, and Java. And after having worked in a traditional application development environment, Sudhindra became part of the pivotal team and built their Kubernetes platform offering. He also has diverse project experience, including building an application for the largest publishing company in Chicago, a large data center automation effort, a large auctioning system, and a voter campaigning application for the U.S. national election. So I guess you've been around a little bit, Sudhindra, huh?
Yeah, a few projects.
That's great. Well, without any further ado, thanks for coming out tonight, and we're looking forward to your talk as well. So please take it away.
Thank you, Ari. Thank you for that introduction. Let me start sharing my screen. I just want to make sure that the right slides are up. Yeah. Okay. Are you able to see my screen? And I'll move to presenter mode. Yeah. Are you able to see my screen? Give me a thumbs up or thumbs down if you can't see it. Great. Thank you guys for having me. And I'm glad to be here. This is my first local meetup. I'm based in the Bay Area. And this is the third time I'm doing this, so I'm hoping that this is much more refined than the first time that I did this, and I was much more nervous at the time. So this is a talk I wrote up about my experience with Golang and dabbling into real concurrency and just understanding how it can be used. And this by no means builds a real application, but it builds the system that builds the real application. So there's a little bit meta stuff going on there. Okay. Yeah, I think, okay. So this is a little bit about me. I currently do more management than writing code. I've done multiple languages, and I came to Golang as a skeptic because I wrote Ruby for a bunch of years, and I found Go to be not so natural to my thinking, and I really took my time to get used to it and get familiar with what it can do really well. So when I was writing this talk, I felt that the talk was becoming quite technical, and I wanted to find a good metaphor to sort of describe the problems that we were facing and explain them in a plain and simple way. And that's when I thought about this movie that I had seen. I don't know if any of you have had a chance to see it, but I would totally recommend it. And here is why I thought it's a good metaphor for when talking about concurrency. As in concurrency, this in this movie, events happen out of order. They're looking for an antagonist who is causing pain, which is what our team was going through. And as with concurrency, all things fall in place in the end. Or as with most concurrency applications, things fall in place. Same thing happens in this movie. So I thought that is a good metaphor. So you'll see some images that are representative of what I felt was appropriate as what happens in the movie versus what we were experiencing. So as things how happen out of order, this talk is also out of order. But as I promised, things will come together at the end. So thank you for being here. Thank you for encouraging me to give this talk. Let's see where we go. A few references just off the bat. You will, if you go through this talk and want to implement something that I talked about, look for the Go programming language book. The effective Go book is really good. Every time I had a problem figuring out how some things work, Golang Playground was really useful because it was able to reproduce the issues that I could face in real code in the Playground context as well. We used a couple of technologies that were part of the Cloud Foundry ecosystem. Bosch is one of them. So we'll talk a little bit about Bosch. And we were building a Kubernetes platform, and we were building it by while using the CI/CD system called Pivotal Concourse. So if you're looking for that, the links are in the presentation. So I should tell you off the bat that we did have success. We actually were fighting a build time that took 6 hours to complete. At the end of this effort, it went down to 2 hours. And which was a 400% improvement. I know you're calculating in your head, it doesn't actually add up to 400% improvement, but I'll explain when we go through this, how it actually became 400%. We were able to trace what was going wrong during a failed build, which was not possible before. And given that we were able to fail fast, that means we were able to fix things faster. So this was overall the impact was positive. Like the character in this movie, he finds his wife's killer. Right. So what were the main characters in our story? Just to reflect, we were building a Kubernetes platform. And this was meant to be, you drop, install it, and then this platform manages the virtual machines, and then you can bring up a Kubernetes platform on it. If you wanted to update that, all you would have to do is update this platform, and all the related libraries and dependencies would be updated. So if there was a CVE in one of the networking components, all you have to do is update our platform, and the CV will be fixed. So you don't have to worry about the hundreds of binaries that came with it, and you don't have to patch it yourself. So we really were proud of the day 2 operation support. Right, day 1 is the easy one where you give them a good install path, but continuing to give them forward compatibility to new bugs, fixes, and patches was where we're really good at. And during this time, when we were working on this, we were starting to support Windows. And if you have used Windows in any cloud scalable Kubernetes way, you would know that it is quite complicated to support Windows itself, right? So that added an extra complexity in terms of how we were building this platform. Another character was that the whole platform was driven by Bosch. Bosch is a service that helps you deploy a cloud, maintain it, scale that cloud, diagnose issues with it, and repair it as well. And Bosch also allows you to deploy things that are compatible with each other. You can build you can ship source code to it, and Bosch will actually build it to the target operating system. So there are some niceties that Bosch does, so that you don't have to do all the hard work all the time, right? And when Bosch does any of these, it also maintains the cache, so that if you are going to do that again and again, like if you're going to spin a similar VM, it doesn't create the image. It just uses the cache and publishes that VM, and so that you get faster scaling. So there are some nice things about Bosch, and it was good to have and leverage its properties. And then to bring this to put it all together, we had a continuous delivery system where we had everything automated. Imagine building such a system that works on Azure, AWS, VMware, vSphere, Red Hat, and GCP. And I'm growing, and we were being asked to publish this for more cloud systems. And one of the things that we were doing, we were supporting n, n-1, n-2, so that people had an upgrade path, so that if they are two versions behind, we would still support them, and they would have an upgrade path from that to the latest, and then get the latest CV fixes and keep their system up to date. At the time we started this project, we had about 49 different acceptance environments or variations, like, oh, you want to build this system with this type of networking on this type of cloud. And networking is one variation, storage type is another variation, etc., right? So we had 49 of them at the time we were building this. So that's quite complex, and every single thing, every single variation takes a number of hours to just bring up, to just invoke. And then once it is invoked, then we are going to run tests on it. So that sort of adds up. And when we have run all these systems, even in parallel, it takes multiple hours. So what was happening? What was going on? Every morning, when we were talking at stand up, this is how it felt. It felt like we were running really, really fast. This character wakes up in the movie and realizes that he's running. And first he thinks that he's running after somebody. In a bit, he realizes that somebody's running for him with a gun in their hand. And that's the kind of feeling I got when I was on this team. And we were running with somebody else pushing us, and that was really not good for the morale, not good for how you build software. And many of the issues were because the build time was so long. Even after we had gone through the build, we would get one binary, which is not necessarily the good binary, because it would fail many times. And then we sort of calculated, and it took about 70 hours minimum to test a tile. A tile was a combination of these binaries, as we called it. And every single failure caused this 70-hour cycle, which was very, very painful, right? And given that it was 6+ hours, sometimes 6 hours, sometimes 7 hours. So you started a build in the morning, and then by the time it's time for you to go home, you have received the result, but you don't have enough time to fix it. And the first gut response is, okay, I'm just going to rerun it. I'll check on it next morning. And that's the cycle that we were going through. And then next morning, again, we would either face the same failure, or we would have an unknown green. We would just have a green, and we wouldn't know why. What went wrong in the previous build? Why is it not reproducible? So we had those issues. We didn't have the transparency. And this is what we were doing. We had a list of dependencies. We had think of that tile containing all these features, and that being combined to work with Bosch to create this Kubernetes platform, right? So for each of these binary, we had to check whether it's already been pre-compiled. Then we can just use it and make the installer tile. If it is pre-compiled, find it in the cache. There's some time to find in the cache. Sometimes we also have it pre-compiled, but it is not in the cache. It is stored in the cloud storage. So we pull it from there. If all of this fails, then we compile it. And the compilation takes a while, because when you're compiling against a Linux version, you're pulling a large Linux stem cell and then building it on top, and then that adds up. So overall, it took about 2 hours to just build the binary. And then we would throw the binary onto different variations, and that process would take 4+ hours. So that is quite long, right? And in all of these places, I think so what would happen was we used to go through these in a sequential manner. And we did not incorporate the optimizations that we could for these different types of latencies. So we are pulling images or binaries from the cloud, and different clouds had different latencies. We were pulling images from our network itself, the internal network, that had its latency. Compilation took its own time. Sometimes just moving from one hard disk to another took some time. And then when we were building something specifically for Windows, because of how it was configured, there was some OS specific latency, right? So there are all these latencies that are actually hurting us, but we have not addressed them, right? And we are trying to find who our John G is. We had some tools that were at our disposal. Something that I was learning at the time and something that we were discussing was how could we leverage concurrency to make this to attack all these different types of concurrency issues that we were having, right? I'll go through a couple of slides on just the basics of concurrency and the one as it applies to what we were doing. Golang actually has a first class primitive called GoRoutines, and they support concurrency, which is not like it's supported in other languages. They are very lightweight threads, or as if you can think of it that way. They are easier to reschedule. They have a very light footprint, and they are supported natively by the language. So it is easier to manage, and Go has some nice semantics around it. And by default, they don't offer any thread local storage. So then a lot of race conditions are eliminated just by the design. Then the other concept that we wanted to leverage was channels, and this is something I learned freshly when I started doing this. So Go encourages you to share memory by communicating instead of sharing memory itself, so that eliminates all the mutexes and lock handling that you have to do. There are a couple of different types of channels that are available, buffered and unbuffered, and buffered obviously means you specify size and you can keep on adding stuff to the channel or messages to the channel. Unbuffered means the size is unspecified, and then your mileage may vary if you send too many things into the channel. So with Go routines and channels, there is as we were brainstorming, we were talking about what is the other concept that we could use to build the entire system, and that is when we found and I think one of the people on our teams knew about it but had never really implemented it. This concept that Go defines as pipelines. Pipelines is a combination of Go routines connected through these channels, where concurrency is or handshake is achieved not by using locks or not by using any gating mechanisms, but just by improving the flow across the system. Right, so you don't have to bookkeep your state. You don't have anything that would cause a race condition, and that's the aim that pipelines has when you build that system. So and it was odd for me at the time when I was learning in the Go programming language book. There's just 1 page or 1.5 page which has a short description and one example, I think, of pipelines. But I learned more by building one on the Golang playground than reading after reading that page. And I think there is more to be said about it than just that. So what about people will ask, what about wait groups or other synchronization mechanisms? Why wouldn't you just use them? Because those are also available in Golang. So this is something that we learned by doing. We already had a couple of places where Go routines were used with async, await kind of things with wait groups, and we're building synchronization around that. And we actually sometimes we ran into deadlocks, and often the culprit was that we forgot to call wait group done, or we did not put the differ in the right place, and a thread was hanging and waiting for something else some other Go routine to finish, and it became a mess. And to avoid this, I think the pipelines technique helps a lot. And when we set out to actually build this pipeline to solve all these issues, we decided that we don't want to forget what we learned about writing good code, writing test. We will continue to write test-driven development. We'll continue to refactor things. We'll continue to focus on encapsulation and separation of concerns and responsibility. How did the new code look like? And let's look at the new code because again we are going out of order. So again, going back to what the basic algorithm was, that we needed to combine a bunch of binaries, and we needed to go through different locations that such a binary might be available. If not, we would need to build it. And if we needed to build it, then we would need to start from a source, find it in cache. If not, then compile and then store it in the cache, and then store it on the cloud, and then form the installer, right? And this was complicated enough for one target OS, and that's when we threw at it another OS, Windows, and this became twice, if not, twice more difficult, right? Because we had to do the same thing over and over, and the algorithm that we had was not able to handle that, because it did not consider all the different latencies that were in the system. So how does the pipeline look? So then once we identified these different latencies, we actually built a pipeline that went from one stage to the other. And when it sent a candidate from one stage to the other, it used channels. And since channels are already a blocking mechanism, they will block until messages have been read on them, and you don't need any other synchronization mechanism. So how did it look? We read the number of releases, or what we call as releases or binaries. Those dependencies, we read them, and we created a bunch of parallelizable either downloader, compiler, or publishers, because those were the activities, those were the blocks that would form the pipeline. Once we created that, we identified what is that object that is going to go through this process. So for each dependency, we called it a release candidate. If that has to be included in the tile, then we need to know the following. We need to know where the binary is, a URL to where it is actually stored. Whether building that or going through that system or going through the flow was a success or a failure. So that if any of this is failure, we can just strip and have fast feedback. And then an embedded result object, which contained the path where the source came from, where the artifact is, and if there was a failure, then the errors would be embedded in this. So this was our encapsulated release candidate object, which maintained the state about that release candidate. I think this was one of the key revelations we had once we had this design in place. That encapsulation really helped nail down the state to where it belonged, and not scattered through the system, not scattered in wait groups and figuring out if this is done or that is done. And we were very aggressive about breaking down things. Like, we broke down the release candidate, we figured out how to handle the bot, how to interact with the BOSH client, how are things going to be stored on the GCS bucket, how do we write the result down, what things need to be part of it. And then we composed the release. So the candidate release included the struct for the result and so on. Right? So we composed these objects to form the objects that we needed. And the most important thing was to identify when will we be done once the releases have flown through this pipeline, because we need a termination condition. Otherwise, since the channels are blocking, they will keep on waiting for the next message, right? So we need to close those channels somewhere. And given that we had a predefined list of dependencies as input, we knew that so many releases or candidates have to come through the pipeline. So we were able to identify the termination condition, right? And at the termination condition, we were able to identify if there are errors, and then trip and signal failure. And once we had processed all this, we were able to close all the all the channels that we were using. So we had a safe termination. So there was no deadlock. So why did we do all this? Why did we spend all the time building this? It was because the old code had the following, right? Every time we had a release or a dependency, this is what happened. We went through each of the different dependency and and you can see that it was already a Go routine that handled each of the dependencies separately. So there was a little bit of concurrency there. But what happened when we called process release? It called process release called download. download called compile, compile called publish. So it was basically a bunch of concurrent routines, but then it became deeply sequential, and it did not address the problem of download has its own dependency, compile has a separate dependency, and publishing has a different dependency. So it did not handle many concurrency opportunities that were in the system. So that's what was hurting about this old way of doing concurrency. Also, the errors were never recorded, or they were recorded as a bunch. Like, so we wouldn't be able to identify that this error happened because of this binary. They were just added into a single object. So it made sense to actually attach the error to the binary that we were building, instead of just collecting all the errors. So that was another transparency issue which we were able to fix during this, and it became obvious when we did the new design, or we were working on the new design, that this was an issue. And so these were some of the issues, like I mentioned, that they were using wait groups, so we had to wait on the synchronization mechanisms. It was mostly sequential, and it did not do the right thing in terms of encapsulation and separating responsibilities, and it didn't have a good it had very didn't have good coupling based on where the data needs to be. And this started breaking as soon as we introduced the new OS, which had its own complexities, right? And it would have ballooned our build time by a factor of 2 at least. And that is the problem that we were able to find, that we found our John G, and we are able to fix that with the new code, as I explained. And so when we reflected on it, what did we change? We made it so that it's easier to read, it's easier to understand. There's no chain of events that is happening, and we don't go down the rabbit hole. We were able to address different types of latencies. We were able to quickly look at the code and see what was going wrong. And this project involved multiple teams. Like, imagine there's a networking team that builds a networking component, storage team that builds a storage component, core Kubernetes team that builds the core Kubernetes controllers, etc., right? So our job was to go and give them feedback if any of the build was broken because of the code they committed. So that made it, this kind of reorganization made it super easy, super transparent, when we can just point to the team where we saw the issue. So how did we measure success? So previously, for one OS and for 10 plus dependencies and 40 plus environments, we were able to build one tile a day. Like I said, 6+ hours, which took our whole working day. When we did this refactoring and added the new OS, we almost doubled the number of binaries, because we had to build it for 2 different things, and the number of environments grew to 100, or more than double, because we also added another cloud provider in between. We were able to produce 4 tiles a day, because we were able to handle these different concurrency. We didn't have the sequential processing, and that means that our efficiency went from 1x to 4x. So that's how we got 400 times better, right? And the fact that it failed in 2 hours means I could do something that same day when I had the context. I had the team sitting right there with me, instead of leaving on a Friday, disappointed, dejected that my last build failed, and then coming back on a Monday and saying, oh, where was I? I don't know what we were doing because the last build had failed and we don't know who to talk to. Right, so that saved a bunch of time. That improved morale quite a bit. We actually started having confidence in our system. We were able to give feedback to the people who we were integrating with, and they were happy that they were getting like errors that they could actually work on. So here are some things that I learned. To not be afraid, take that opportunity to refactor. Do remember to go back to basics. Test driving this helped us a lot. Learning via Go Playground helped us a lot. We were actually able to reproduce some deadlocks that would have happened in our code by writing tests, which was amazing. I had not done that before. And sometimes this kind of tech debt gets deprioritized in the beginning, and there'll be a time when there is no choice, and it will get prioritized. So wait for that moment. As soon as you get that moment, seize it and run with it. Right. That is the time for to solve these kinds of tricky problems, and that is what makes engineers happy. Also, don't be afraid to ask for support. When I actually started working on this, I had about 6 months of Golang programming experience, and the only Go routine I had written was a minor refactoring to the old code that you saw, and I had only read and practiced Go, but never really written production level code. But I had a couple of people on my team, Kevin and Adrian, who encouraged me to do this, and they were there to support support me in making the shift from my Ruby thinking to Go thinking, which I'm really appreciative of. So find such people. I think there will be some on your team, and don't be afraid to try new things. So if you want to take anything away from this talk, then learn about Go routines, learn about how you can do the concurrency using async wait groups. Try it, build it for yourself, learn about channels, learn about pipelines, convert that same thing that you built with async wait groups into channels and pipelines, and see for yourself, right? And as a challenge is build a real application without using the old school synchronization constructs. It will it will feel different. It will feel like you have been liberated in some sense of managing these things. That's all I had, and I hope you enjoyed the talk. Any questions?
Well, Sudhendra, thank you very much. If anyone has some questions, please, if you want to either put them in the chat, or if you want to go ahead and take yourself off mute. But Sudhendra, would you like to get a drink of water?
Yes, I will get some.
Yes, before you answer questions, I think that's more than just a. I was impressed that you could go that long without the water, but he'll do that. But does anyone have any questions for Sudhendra this evening? Questionless.
Hey, and if you don't have any questions now, you can reach out to me via Twitter. I think there's somebody raised their hand.
Yeah, go ahead, JPAP.
Hey, Sudhendra, thanks for the talk. My question really relates to the amount of concurrency that you're processing at any one time. So, you can launch a bunch of Go routines and they all run concurrently. They can block, they can do some work. It kind of depends on what you're doing, right? It sounds like the amount of concurrency that you have in the system is maybe not that great. You sort of had it on that slide where you had the triangle going down. I think you had some figures there. Yeah. The question really is in your situation, did you not have that much concurrency where you had to worry about the number of Go routines and the number of things that you're doing in terms of, system resource, memory utilization or something like that? And if you did, what did you do to limit the amount of concurrency so you don't blow up in terms of resource use?
That is an excellent question. And we did by failing. So yes, we had resource issues, at least in the beginning. So I'll go back to one slide where I'll show you. Yeah. So there is concurrency that you can put where. One thing I want to mention is all the concurrency opportunities that I had in my system were not related to moving data locally or handling data locally. It was about getting it from the network, getting it from this resource and that resource, right? And one of them was Bosch, for example. And if you don't have enough Bosch directors, you are limited in how many concurrent routines you can run or effective. So that is the first roadblock we hit. We had one Bosch director and we started throwing routines at it. So that became the blocker. So we scaled that. We scaled Bosch and started bringing up multiple Bosch directors. So that helped. With the yes, and the other thing that we tuned was the VM or the container that actually brought up that Concourse brought up. that had to be tuned so that it gets many more cores than we had before. So I don't remember how many it finally got. I think it was more than 4, because I think we had one with 2 cores and one with 4 cores, but then we had to go up to 8 cores, at least when I was tuning it. So there was some.
So you didn't have to limit concurrency in your case. You kind of had unlimited resource. You could just, go as parallel as possible. Did you ever have to, constrain how much parallelism you used, and how did you do that in that case?
Yeah, so we, given that we were only handling, so like, see how we were handling 10 binaries and 10 binaries, so 10 routines, right? So we didn't have to limit that much, or we didn't hit the boundaries, I think. So, and going to 20 binaries didn't give us, we didn't make us hit the boundaries. So the constraints were, like I mentioned, they were in the BOSH director, or anytime we hit the network, and there were some things we could do about it, and some things we couldn't.
I see. Thank you. You're very lucky you didn't have to constrain yourself, it sounds.
Yeah, thank you.
Any other questions for Sudhindra? Okay. Well, thank you so much. I really appreciate that, you coming out and sharing with us, Sudhindra. That was really a great talk. And if and Sudhindra, you're on social media if people want to reach out to you on LinkedIn and Twitter if there's any additional questions after.